Today we're going to talk about the differential amplifier. The differential amplifier is basically the input stage to an operational amplifier. You're going to do the operational amplifier in Electronics 3. But please remember, you must first pass Electronics 2 before you can do Electronics 3. Now, if we look at this differential amplifier, they try to manufacture these things in such a way that Q1 and Q2 are basically identical. They can never succeed to manufacture them 100% identical, but they try to get them as close as possible to identical. If you look further on the circuit, you will notice we got a VCC. That is my positive supply, and we got a minus VEE. That is my negative supply. I'm going to give you an indication how to manufacture or build a split supply. We call this a split supply. I'm going to give you a drawing on the screen. Check and take it down. Now I use two batteries. The one battery is 15 volts, the other one is also 15 volts. They connected in series. The supply is like follows: positive, negative, positive, negative. They are coupled basically in series. This center point is called my 0 volts. This will be plus 15 volts. That will be minus 15 volts. How do we measure? We always measure with respect to my reference. If I take a multimeter, I put the black lead on the 0 volts and the red lead on the plus 15. My multimeter should read plus 15 volts. If I put the black lead on the 0 volts and the red lead on the minus 15 volts, my meter should read minus 15 volts. That means we always measure with respect to my reference. That is a split supply. And you must always remember, we work with conventional current. Conventional current flow from positive to negative. If you put the black lead of your multimeter on the minus 15 point, and the red lead on the plus 15, you should measure 30 volts, not 0 volts. Some students will tell you you will measure 0, you will measure a total of 30 volts. I will also give you another way of explaining this. On this line, you also notice my 0 volts is my reference, and if I measure from 0 to in the direction, I will measure minus 15. One thing I want to point out, if I look at this 0 volts here, what can I say about the 0 volts compared to minus 15? I can say that 0 volts is more positive than minus 15. What is 0 with respect to plus 15? 0 is negative with respect to plus 15. All right, I'm going to explain the operation of this differential amplifier. I'm going to put two exactly the same inputs. I'm going to make input 1 I connect input 1 to 0 volts. I connect input 2 also to 0 volts. Now we can say what's going to happen in this circuit. Will the transistors Q1 and Q2 switch? Now we must go and have a look if they're going to switch. Now let's have a look. We know to switch on a transistor, you have to forward bias the base emitter junction. Now let's have a look. Are those base emitter junctions forward biased? Yes or no? Now to forward bias it, there must be a current flow from the base to the emitter. Now, one very important thing to keep in mind. My emitter is connected to a negative supply. That minus VEE, or the minus, let's assume the minus 15. Now, my base being connected to 0 volts. What is 0 volts with respect to the minus 15? 0 is positive with respect to the minus 15. That means we will get a current that's going to flow like that. In at the base, out at the emitter, through RE to my negative supply. That is for Q1. That is going to cause another current to flow through the collector down to my emitter. That will be my collector current. Let's have a look on the other side. Also 0 volts on Q2. That's going to cause a current to flow like that. That is my base emitter current. It's forward biased. And then we're going to get a larger current that's going to flow. The collector emitter current is going to flow like that. That means both those transistors switch. That means if I measure now from output 1 to my reference, I will measure a voltage. If I measure from output 2 to my reference, I will measure a voltage. Now what can I say about those voltages? If we assume the two transistors are identical, that means the voltage at output 1 and the voltage at output 2 should measure exactly the same. Because the volt drop across RC1 and the volt drop across RC2 is also going to be exactly the same. If I measure from output 1, let's say I put a voltmeter in here, like that. From output 1 to output 2, what should that voltmeter read? Because the voltages at 1 and 2 is exactly the same, the voltage difference there should be 0. That means that voltmeter in this case should be measured 0 volts. Alright, that is for the first part of the work. If you look at page 290, there they show us IE1 is equal to IE2. Then I can also say IE1 is equal to IE2 is equal to IRE. IRE is the current flow through my emitter resistance divided by 2. And because the base current is so small, I can also make the statement stating that IC is approximately equal to IE. That means I can make the statement say IC is approximately equal to IE. Because my beta values is normally fairly large. And the voltage at this base here, the base emitter voltage for a silicon transistor is always 0,7 volts when the transistor being switched. The same for Q2, that will also be 0,7 volts. That means if I got a negative supply, let's say of minus 15 volts, then I will have a voltage at that point there of minus 14,3 volts. That's quite important to remember that the voltage at that point should be minus 14,3 volts if my supply is minus 15, my minus VEE. We're going to consider figure 6.38, the basic operation of a differential amplifier. Ground is 0 volts, showing relative change in voltages. All right, we basically had a look at this already. We have got an idea what's going on. Now this is the same one we did previously. You can see in both cases, both the inputs being grounded. Now you can see, we look at VC1 and VC2. In this case, VC1 and VC2 is going to be equal. IE1 and IE2 is also going to be equal. IC1 and IC2 is also going to be equal. That means both of those outputs will give me a certain output voltage, and that should be the same. If I measure between 0.1 and 0.2, as previously mentioned, that voltage should be equal to 0 volts. Let's go to figure B. If we consider figure B, we will notice the one input of Q2 is connected to my reference, and the other one is connected to a DC voltage, a positive DC voltage. Here we talk about normally a single-ended input. Why a single-ended input? Because the other input is connected to my reference. Now we know, if we consider input 1, that is connected to a positive voltage. That means if I can look at IB1 of Q1, the base current of Q1, let's gonna put this in red color. I can say that this base current is going to be larger than the base current of Q2. All right. That's also going to give me a IC1 current. That IC1 current is also going to be larger than IC2. Now, when that current is larger, I can say that the volt drop across RC1. How do we calculate volt drop? Everybody in this class know Ohm's law. I can say that IC1 is equal to, all right, now let's rather calculate the voltage. Let's calculate the voltage across that resistor. Now I can say VRC1. The voltage drop across RC1 is equal to IC1 times RC. Everybody knows that. That's Ohm's law. We apply Ohm's law, we can calculate that volt drop. Now, the volt drop across RC1 is going to be larger than the volt drop across RC2. That means the volt drop across the transistor is going to be smaller. That's why VC1 is going to be smaller than VC2. Because what's going to happen? The current on the left-hand side is going to increase. The current on the right-hand side is going to decrease. Let's go and look on the right-hand side. That base is connected to 0 volts. That means that transistor is going to switch. That means here I will have a base current flowing like that. And I will have a collector current flowing like that in the black. But now, if I calculate VRC2, I can say VRC2 is equal to IC2 times RC2. Alright, RC2 and RC1 will have the same resistance, doesn't matter. But now, because IC2 is smaller than IC1, the volt drop across VRC2 is going to be smaller than the volt drop across VRC1. And that's going to cause this current to be smaller, and that's why the volt drop across the transistor is going to be larger. The volt drop across VRC2 is going to be smaller than the volt drop across VRC1. Alright, that is basically what's going to happen. If we go and look at figure C, what's going to happen there? There we turn it around. We put Q1 connected to my reference, or 0 volts, and we connect Q2 base to a positive voltage. That means this IB2 is going to be larger. That means IC2 is going to be larger, and IC1 is going to be less. And that's why the output measured across the transistor of Q1 will be larger, and the volt drop across Q2 is going to be smaller. Because we must remember, if we consider this whole circuit here and we think about Kirchhoff's voltage law, a very important law. If I put the following values in here, for example, I make the supply here plus 15 volts, I make VEE minus 15 volts, and now I know across this whole circuit, what is the volt drop across the complete circuit? It's going to be 30 volts. That means if I go and calculate VRC1, VCE of Q1, and VRE, if I add up all those voltages, I should get 30 volts. The same on the other side. If I add VR2, VCE of Q2, and VRE, I should also get 30 volts. That means, please take note, you can't get more or larger voltage than your supply. That is always very, very important. Now we're going to look at modes of signal operation. The first one we're going to talk about is single-ended differential input. That is on page 292 in your books. If you look on page 292 in your books, we talk about a single-ended input. Now, why we call it a single-ended input? You will notice that input 2 of Q2 is connected to my reference, and the other one I put a signal in there. And you will also notice that these two signals at the outputs are basically 180 degrees out of phase. The next one, figure B, that's also a single-ended input, but in this case, input 1 is connected to my reference, and input 2 is connected to AC source. That's also a single-ended input. All right, the next one, there we've got a double-ended differential operation. Now, if I look at a double-ended differential operation, that means I got both the inputs, and the two inputs I apply. There's the input 1 and there's the input 2. Those two inputs are basically connected 180 degrees out of phase. My outputs will also be 180 degrees out of phase, but it will be equal to my peak values. All right, no, sorry, that is not for differential input, that is for a single-ended input. If I look at the single-ended input, figure B, if I look at figure B, my single-ended input, I also got a single-ended input, and then that will be equal to my peak values, and those two will be 180 degrees out of phase. All right, here we're going to look at there's also a single-ended input. That figure there is figure C is also a single-ended input. Input 1 is connected to my reference, and input 2 is my input signal there, and the two outputs will be 180 degrees out of phase, and will go also to my peak value. If I go and look at the differential operation, here I've got a differential operation, figure D. If you look at figure D, you will notice I got both inputs there. The two inputs are how many degrees out of phase? 180 degrees out of phase. Then my outputs will also be 180 degrees out of phase, but it will go to 2 times the peak value. All right, common mode operation. Common mode operation, we'll talk a lot about common mode operation electronics 3. Common mode operation, both the signals to my inputs are basically in phase. You will notice input 1 and input 2 are basically in phase. Figure D here is also a single-ended input. We already talked about that. Another single-ended input. We already talked about that. But now figure D here is basically common mode. Now if we look at the common mode, I repeat, both my inputs are basically in phase. Now when they're in phase, they will basically cancel out and my outputs will basically cancel out. That means my differential output will basically be 0 in the case of a common mode signal. Now common mode is very important because if we go working in electronics 3, what happens in the case of a common mode? If I want to amplify a signal, you know normally you amplify a signal, and if I look at the signal, the following will happen. Let's say I've got a sine wave and I want to amplify this sine wave. Now that's a very nice sine wave. But normally we will find that there's noise on the sine wave. That means superimposed on the sine wave, there's noise. And you normally don't want to amplify your noise. If you've got an amplifier and you amplify the noise, it's going to be basically irritating to the ear. You don't want to amplify noise. Now if I got a connection like this common mode, what actually will happen, due to the common mode, the noise will be basically connected to both the inputs, or will be situated at both the inputs. Now what will happen, the amplifier will basically eliminate that noise. And here you can see they talk about a resulting of a 0 volt AC. That means that's what's going to happen. And that brings us to basically the next part where they're going to talk about common mode rejection ratio. Now each amplifier, if you're going to look at the op amp, they will give you a common mode rejection ratio. Now my common mode rejection ratio is basically the following. I'm going to write it down here and we're going to talk about it. That's my common mode rejection ratio, and that is equal to AV. Everybody in this class already knows what's AV. Differential divided by AV common mode. Normally, this differential voltage gain for a 741, you're not going to use it in electronics 2, but you're going to use it in electronics 3. The gain of that is around about 200,000. You can see that's a very high gain. And the common mode gain will be in the region of around about, let's say, 0.2. That will be a very low gain. That means my common mode rejection ratio is normally a very high value. We can also express that in decibels. When I express in decibels, my common mode rejection ratio is equal to 20 log AV differential divided by AV common mode. All right. That is basically all we're going to do. We're going to look at this example. There's example 6.13. They state a certain differential op amp has a differential voltage gain of 2000 and a common mode gain of 0.2. Determine the common mode rejection and express it in decibels. All right, they give us the gain, the common mode, the differential gain of 2000, the common mode gain of 0.2. My common mode rejection ratio is equal to my differential voltage gain divided by my common mode gain. That's 2000 divided by 0.2, and that is equal to 10,000. You can see it's a high value. Expressed in decibels, it's 20 log of 10,000 will give me 80 decibels. All right, that is all what I'm now going to discuss now. I will come to the class and ask if there's any questions.